Yeah, I'd like to tell you about laser communications. As Bruce said, I worked for quite a large number of aerospace companies. I worked for Lockheed Martin, I worked for Boeing up in Seattle, and I worked for Ball Aerospace in Boulder. And in all three of those places I was involved with lasers, doing different things. But the one project that I spent the most time on was laser communications. There were a lot of different programs and projects that we had. We did things for NASA, for example, but did studies. And one of the studies we did was to come up with a communication system that would allow communicating all the way from Earth to Pluto, or Pluto to Earth more likely, is to put a small laser communication unit on a satellite. It had to be small because weight is at a premium on any sort of a spacecraft. You want to minimize the amount of mass or the amount of weight, and laser communication offered that prospect. It is able to allow or permit communications from Pluto, which of course is no longer a planet, but it's out there. It's 40 astronomical units from the sun. We're only one, so it's 39 times 39 million miles from Earth all the way to Pluto. And we needed a small compact system to do that. Radio systems are good for a lot of things, but for long distances like that, they're not very good. The problem is that radio waves produce beams that spread out over a huge area. And light beams, having a smaller wavelength and a higher frequency, they tend to be more confined. So we were able to come up with the calculations and the modeling to show that it was possible to have a very small optical system with a telescope no more than 4 or 5 inches in diameter, and to operate on no more than about 5 watts of power to communicate all the way from Pluto to the Earth. Think about that. Your cell phone also uses maybe 5 watts of power, something like that. But it spreads waves out in every direction, whereas with a laser communication system, you can be highly directive. And one other system that I worked on too that was very interesting, I thought, was the astronauts well, sometimes would spacewalk and they'd be floating around outside of the space station. And there was a need, of course, to communicate with them. And unfortunately, radio was not an option. You would think so for short distances and things, but it turns out that the frequencies that were optimum were already owned by, of all places, Walmart, and it was not possible. So we ended up developing a small system that an astronaut could carry, and the problem with lasers in that respect is they're very directional. So we had to come up with a way to spread the light out everywhere, so that no matter which orientation the astronaut had, light would go out to the receiver and they would communicate. And I ended up with a patent for that, for taking a laser beam and causing light to be spread out omnidirectionally. This has been around for an awful long time. You know, fire signals were used, smoke signals were used, and Alexander Graham Bell, who's most famous for inventing the telephone, actually invented a photophone, which he thought was his best invention. He thought that was going to be wildly more popular than just ordinary telephones. But it works on sunlight. There's a blinker system still used on ships. Turn signals and stoplights, if you've ever thought about it, that's really a form of optical communications. But one of the big advantages is that light operates at extremely high frequencies. The amount of data you can impose on a signal depends upon its frequency. The higher the frequency, the more data. Optical frequencies are like 10 to the 14th, 10 to the 15th hertz, very high. So they have theoretically a very high potential for carrying extremely large amounts of data, much more than radio waves, which are at lower frequencies. Optical systems operate up here in this range, and if you had a modulation frequency of 10 to the 12th, and modulation frequency is a way of imposing information on that so-called carrier signal. 10 to the 12th, this is like a terabit if you got 1 bit for each of your cycles here. But this would only occupy about 1/10 of 1% of this bandwidth. And modulation frequency, this high is about what would be possible to carry about 1,000 cell phones conversations all at one time. You know, they're about by 10 to the 9th or so. They operate at that frequency. The beam size, which is very important, depends upon frequency, like I said, or wavelength, and the beam doesn't spread out much, so as a result, you get some very interesting advantages here. Take, for example, a 10-centimeter telescope, 4 inches in diameter, operating at normal light frequencies, which is a little bit low, is about 1,000,000 times greater than a radio system with a 10-meter dish, which is like 33 feet in diameter, operating at 10 to the 9th. Unfortunately, at this time, there is not electronics that can take full advantage of the possible frequency bandwidth of light. We cannot build electronics yet that can go at 10 to the 14th or 10 to the 15th. We're orders of magnitudes less. So maybe someday in the future, some smart people off in the future may invent some modulators that might be able to approach those high speeds and as a result use the full capacity and potential of light waves for carrying information. You know, just a block diagram of what does it really consist of. First, it starts with a laser. You need a modulator, and there are a lot of ways to modulate. There are a lot of ways to put information on a carrier wave. But I'll talk about the simplest one. You have a driver to run this, and you know, theoretically, all you're interested in is sending this information at point A to point B, and if you've done a good job, this is going to be a very good copy of this over here, although it's never possible to have perfect congruence between these two. Anyway, you have a transmitter, which consists of a telescope usually, and at the other end you have another telescope, and you have an optical detector of some sort, and some of those are very fast, but not quite up to the speed of the intrinsic frequency of light. Then you have a bunch of electronics and stuff, and then you demodulate, and most of the communications these days is digital, not analog. And the simplest way to modulate a signal with a laser is just to turn it on and off. Like if you are sending a digital signal, when the laser is on, that might represent a 1 bit. If it's off for that period of time, it might represent a 0 bit. And you can do this very fast with a laser. You can modulate the laser so it turns on and off millions of times, maybe billions of times per second. But because there are many sources of noise in the environment and in the electronics, the received signal is not everything that you would hope it to be. It's somewhat contaminated or degraded. In engineering, you're always talking about the signal-to-noise ratio, which is very important. And I have some more to say about that a little bit later. Systems are designed to operate with a maximum allowed bit error rate, which might be only 1 bit per million bits. If you send out 1,000,000 bits, you want to build a system that is good enough so that only 1 bit out of that whole million is in error. Communications is really a discipline filled with the need for probability and statistical concepts. You know, like for example, did you ever think about what is information? You know, if you're at the other end of that system and you sit there and you see symbols coming in, and if they're very much what you would expect to have happen, like a repetitious signal, there's really no new information there at all. But if you send a set of symbols to the other end that you thought were improbable, that constitutes a huge amount of information. So you have to think about what is information when you think about these kind of systems. It's very, the space is very benign as long as a planet or a moon doesn't get in your way if you're transmitting from point A to point B. But there are other applications where you might want to operate a system like this in the atmosphere. And that makes it much more difficult, not impossible, but much more difficult, because undesirable effects happen to the light as it's transmitted from point A to point B. if you've ever looked up at the night at a star, for example, it twinkles. And why does it twinkle? It's not the star itself that's twinkling, it's because the atmosphere is turbulent, it's moving and it's changing. And as a result, it appears to twinkle. And you get the same sort of effect, even worse than that, if you propagate a laser beam over a long distance through the atmosphere. Things like you point it at point A, but sometimes it's going to randomly go in different places. The beam gets bigger, and what you really desire in an optical sense is to have plane waves enter the receive system at the other end. But as light propagates through the atmosphere, there are warm cells of air and cold cells of air, causing the index of refraction to be different in those different cells. And as a result, by the time the light gets there, it no longer looks like a flat plane wave. Light gets absorbed in the atmosphere. There's Rayleigh scattering, mostly by nitrogen in the atmosphere. And this is why the sky is blue, if you didn't know. It's Rayleigh scattering. If your girlfriend asks you, why is the sky blue, you say it's Rayleigh scattering. Then there's other scattering, which involves larger particles. And these things tend to degrade the laser beam being propagated. There's the absorption. Some of the light is absorbed. For example, sunlight, when it hits the upper atmosphere, is about 1,400 watts per square meter. But on a clear day, the clearest day you've ever seen in your life, if you had the sun directly above you, only about 1,000 watts or so per square meter would actually hit the ground. So like 400 watts, more than a third, about a third, of the power is actually absorbed by the atmosphere. So this would happen with would also happen with a laser beam. If you look at the spectral analysis for the atmosphere and try to propagate different wavelengths of electromagnetic radiation, you find that there are some windows that are optimum, where if you can operate at those, there'd be very little absorption. Others, it's very difficult. This is transmission, so these places over here, where you go all the way up to 100%, would be very good. These would be very bad down here, because you propagate a large, powerful laser beam from here to there, and it gets all absorbed in the atmosphere, and nothing much arrives at the other end. And absorption depends on water vapor, carbon dioxide, humidity, and whatever else. You look at the wavelengths that are good here. In order to have a good laser communication system through the atmosphere, you'd want to try to pick out wavelengths like these, and a lot of those are in the infrared. And as a result, you would need some sort of an infrared laser, which is not always possible at the optimum wavelengths. There are a lot of sort of empirical equations that work to tell you how much is going to be absorbed, how much is going to be scattered. It has to do with the so-called extinction coefficient. But you can look, just optically, if you were trying to communicate over here in heavy smoke, that bit error rate would be like 10 to the minus third, meaning like 1 bit out of every 1,000 is probably an error. Weaker is 10 to the minus fourth, and 10 to the minus 8 were the optical channel that you're propagating through is much better. Like one bit in 10 to the 8th, like 100 million would be an error. And those numbers are readily possible as long as the channel is good. And here's what's really happening, speaking of probability. When you send a 0, for example, the probable signal you might receive might look like this. This would be called the conditional probability, conditioned on the transmission of a 0, and this one would be the conditional probability conditioned on the probability of sending a 1. And when these come in, you have to, the decoder at the other end has to decide, was it a 0 cent or was it 1 cent? And what you usually do, it's called threshold detection. You decide at this point here where the two intersect that if anything's to the right of that, I'm going to decode that as a 1. If anything happens to the left of that, I'm going to code that as a 0. But look at all of this overlap. You could say that if you received a signal, there is some probability that 0 may produce a signal that falls over here. And as a result, that would constitute an error. And it would work the other way here too. You might try to decide that anything to the left is a 1, but there's a lot of 0 stuff over here. So this would represent a very difficult situation where you have a high noise and lots of overlap between these two probability densities. But if life is good and your channel is great, you're going to end up with two probability densities that look more like this, where this overlap area is very, very small, in which case the bit error rate is going to be very, very small. And if you want to memorize this, this is one of the formulas used to calculate the bit error rate. Looks something like that. And it depends upon your signal to noise ratio. The more of that you've got, the better off you are. Curves showing how much power you need. Looking down here, transmit power, this is in watts. This would be like 100 watts here, like 1,000 watts, 1 kilowatt up here. How much do you need in order to successfully transmit with a given bit error rate? So a lot of this is empirical, but it seems to work. In the aerospace business, a lot of what I did was advanced programs, which was thinking about stuff that was off in the future. My one job was to work on stuff that would be profitable to the company 15 years in the future. So we could sit around a big table like this and put our feet up on the desk and throw out all these wild and crazy ideas. We had engineers and physicists, even had a science fiction writer on this team thinking about these wild and crazy ideas. And we would come up with these ideas, and if we all thought it was kind of reasonable, we'd go off then, not try to build a system, because some of them would cost billions of dollars to build them. What we would invariably do is go off and build computer models of these systems and then play with all of the parameters to see how the performance varied. And that was a very interesting part. I used to build an awful lot of models in MATLAB, for example. I used that almost exclusively. It's very good for building models. Throw in all of these equations and things and everything that you understand about the problem and see how it works. And that was much, much cheaper than actually building the hardware to test out the system. Some of these systems, other than laser communications, in this group that I was in, some of those systems would have cost trillions of dollars. We had a unit. In engineering, you want to know about performance, but you also want to know about cost. And we had a cost for some of these systems that we could only give in terms of GNPs, how many gross national products of the whole country would it take to build this system. And usually, of course, none of those got built. The system that I did work on too, it was having a satellite in space that would shine laser beams down to the ocean. Not as a narrow little beam, but one that spread out that would cover hundreds of thousands of square miles. And why would you want to do that? Well, if you had to have the right wavelength, that light goes down through the seawater, and radio waves don't. The higher the frequency of radio waves, the shallower the depth they go down, the skin effect it's called. But laser at the right wavelength can go down hundreds of meters, if it's at the right wavelength. If you've ever looked at plankton in the ocean, it gives off a light sometimes. And it's that light, I guess by evolution, these plankton have found a way to communicate with other plankton. But why we wanted to do this, or why the government was thinking about doing this, or why the Navy was thinking about doing this, was to communicate with submarines that were down underwater. Because they can't be communicated with by radio. It's not possible. Unless they float up a buoy, it comes to the surface, and then they're able to receive radio frequency signals. There were a couple of other systems up in upper Wisconsin and Michigan that were extremely low frequency systems, like 10 or 15 hertz, or cycles per second. And those are capable of going quite a ways down, but at that low bandwidth, you cannot carry very much information. All you could do is, if you want to talk to a submarine, is maybe say, okay, time to come up and let's talk. And that's all. But with laser communication, you could actually carry on, conversations like at the speed of a lot of Wi-Fi networks carry these days. So that was one that would have cost many, many, many billions of dollars. So it was never built. Here are some of the possible wavelengths produced by various common lasers. This is a neodymium YAG laser. This is like a CO2 laser. And what you're worried about is fades. Sometimes the signal gets weaker or stronger because of the atmospheric effects. And the longer wavelengths actually work better. You can't see anything in illumination at 10.6 microns, but it's a very powerful laser. In fact, they use those for doing laser cutting and things like that. In fact, I've seen videos where CO2 lasers are demonstrated. You turn it on, and off in some distance there's a meat cleaver, thick metal, steel, maybe that thick, and all of a sudden the meat cleaver starts turning red and starts turning white, and then the molten steel starts dripping down. Very powerful. But this is the kind of laser I worked with primarily, and we built some of those neodymium YAG lasers. And its natural wavelength is twice that, but if you have some kind of crystals, they're called frequency doubling crystals, that you put in there, that doubles the frequency of the light, and you come out with a wavelength that's half as big. One of the things that helps trying to mitigate some of the effects of the atmosphere is to have a fairly large aperture. The bigger the aperture, the more you're averaging out the irregularities in the wavefront as it comes in. It's not going to be a flat one, but it's going to be irregular. And in that large aperture, some that are going this way are compensated by some that go that way, and as a result, you get a much better result. In fact, this is how adaptive optics works, which is one of the things that's sometimes used or thought about being used for atmospheric laser communications. This is one like down in New Mexico at Kirtland Air Force Base. I got to work with somebody who was really a pioneer in adaptive optics. He demonstrated for me what you can do with astronomy, and almost all observatories now have adaptive optics, and that is to take out the degrading effects of the atmosphere. What you do, originally anyway, was you shoot a laser beam up to the ionosphere, up to the sodium layer actually, and there's a spot of light that's formed up there on that sodium layer, and it goes up through the turbulent atmosphere, and it sends light back down. You catch some of that light, and you can sense how irregular that light is, and then you have an adaptive mirror, a mirror that has actuators in it that can be deformed. It's a deformable mirror, and you can take out these irregularities and end up with a flat wavefront again, which is what you want. Yes, sir?
I communicated with them as well. I guess they have some issue with the rate at which they can compensate for the turbulence.
Yeah, but fortunately, atmospheric turbulence is pretty slow according to electronics, but that could be a problem. Most of the variations you see in the atmosphere are maybe 100, 200 times per second, something like that. And these deformable mirrors can go much faster than that. But maybe in some situations that might be a problem. But he demonstrated to me, there's an observatory called Starfire right on the Air Force Base there. He pointed the telescope right at Betelgeuse, which is up there in Orion. It's a big, gigantic red giant, much bigger than our sun. In fact, if it replaced our sun, we would be inside of it. It's that big. And anyway, he showed that, had the adaptive optics turning off, and you could look at the image plane where the image was being formed. You would expect it to be like a perfect point, but it never is because of the optics and diffraction and all of that. Anyway, it was moving around like crazy, and it was changing shape like that, and all of a sudden he flipped the switch, and all of a sudden it just instantly went to a fixed position, and the shape became very stable, and turned on the adaptive optics.
But they use semic polynomial polynomials
Do we use what?
Zernike polynomials?
Zernike polynomials are used to describe all of the aberrations in the light. You know, there are about 6 or 8 different aberrations that you want to compensate for. Well, the worst one is tip tilt. We actually have a device for the observatory that will take out this one. This constitutes, like, I don't know, 65–70% of the aberration if the light is causing your image to wander around like this. If you can detect that in some other way and tip your mirror to make the image fixed at one point, this takes you a long way towards correcting. You know, we're not shooting up laser beams or anything like that, and we still have that. We haven't used it much, but almost every observatory now does that, and most of them do it actually in the infrared because it's much easier to do at longer wavelengths than it is with shorter wavelengths. There's free space communications, and then now a lot of the things that were learned there are actually used for fiber optic communications. You know, on one fiber, which is really glass, you can send a signal that could simultaneously carry every single phone call going on in a whole country at any one time. And one fiber, that's possible. And they go, you know, from the East Coast, they go to Europe. They go from the West Coast, they go to Asia. They're laid down under the ocean, not single fibers, but big cables having many, many fibers in them, so you have many, many possible channels. So a lot of the things that we use today involve optical fibers. Everybody, someday it's been said, will have an optical fiber running to their house. You'll have a huge amount of bandwidth for your Wi-Fi when that happens, I can tell you. And these are free space, meaning you know, no atmosphere to deal with. There are satellites up around space. If you want to talk to somebody on the other side of the world, for example, how do you do that? Well, one way is to have 3 satellites. You know, like one here, and one here. And if you want to talk from here over to, well, not from here, but from here over to here, for example. That's not a very good drawing. It should be further out. More like this. You know, if you want to talk from here over to here, you might send the signal from here and then have it go that way. But there is a little bit of a delay, not much, but that is one way of doing it rather than, you know, laying a fiber to go directly all the way around the world, which would be a long, long way, 12,000 miles or so. So that's one way of doing it. And there are other satellites, let's say, that are up there that take lots of pictures. And you know how slow or how long it takes sometimes to download pictures on the internet. Well, this is one place where laser communications excels because it can handle much more data. And a lot of these satellites up here taking pictures do a so-called downlink to some ground station down here. They're all in geostationary position, so they're at some fixed position above the Earth. You know, they're out there in those positions. They're geostationary. Geosynchronous just means that they have the same orbital period as the Earth, the 24 hours approximately, but geostationary means that they're up there and they are fixed above this point. This is why your TV dish antennas just point up to the same spot in space, all because the Earth is rotating and the satellite is moving at the same speed angularly. Very interesting. My friend, colleague, and my PhD advisor is an expert on this. I borrowed a couple of these slides from him, as a matter of fact. He's an expert on what you can do about atmospheric turbulence, which is really a science that is not very well determined. We have mathematical equations, mainly empirical, that seem to work. But I should mention also, we have also had some students do some work with laser communications. had a system set up so that from the top of the engineering building and actually from the top of this building, we actually shot laser beams all the way out to the observatory, which is about 10 kilometers. You know, as the photon flies, it's about 10 kilometers. And you collect light out there. And what we're mainly interested in was looking at the signal, how it varied in time, and coming up with probability density functions that would describe these variations. There are different functions that describe turbulence when it's fairly weak. When it gets stronger, you have to go to a different canonical form. So that's still kind of a wide open space. He wants to, if we could ever get funding, he would like to do an experiment from the top of Pikes Peak down to the observatory, which is a long distance, because they have some new theories called non-Kolmogorov theory. Most of the stuff that we think we know about turbulence is described by Kolmogorov, Russian, who were into this subject very big time. And there's some new stuff that we could actually test if we had a path length from the top of Pikes Peak down to the observatory. Things that is nice about, like the case I was mentioning with the space station, the government does not regulate the frequencies that can be used. You know, they have nothing to say about whether you use red light or green light or whatever. Take your pick. So that is another nice feature. There are systems you can buy, mostly, that do things like communicate from oil platforms out on the ocean back to the shore. And in that case, you don't need to worry about what frequency you're operating on, which is a big problem if you're not using light. Almost every piece of the electromagnetic spectrum has been spoken for, is owned by somebody.